We are now going to summarize the various conditions of collisions, namely the energy considerations. We'll do it without numbers, but just so you can understand qualitatively what happens from elastic to inelastic. So, consider again then an elastic collision. So we have the kinetic energy versus time, and we have force versus separation. All right, so what does it look like? When the separation becomes less and less to minimum separation, the force goes up, as you can see. The manner in which the force goes up just depends on the nature of the situation. So I am not showing a straight line here because it may be more complicated. Usually it is more complicated than that, but it doesn't really matter. This is the path, basically, of the force as you diminish the separation. So here comes the two objects as they collide. This is kind of showing what the force is doing to minimum separation. And then, on the way out, it follows the same path. This is the same path going out as what came in. And we've already done an analysis of that. Okay, so the area underneath this force separation graph. Remember, force times, this is a meters, newtons times meters. This is work. This corresponds to energy. It's internal energy, and that internal energy is potential. It's stored potential energy. All right. So that's what the area under the graph is. So we have the kinetic energy, dips down, and total before and after is the same. But you notice that there is a kinetic energy of the center of mass. That's the kinetic energy of the center of mass. Remember, for momentum, the velocity of the center of mass is constant right through the collision. So if we figure out the kinetic energy of the center of mass, that's at this point, because both masses are moving at the same speed, that kinetic energy of the center mass is a constant. I know it's the first time you've heard that, but it makes sense, right? Since the velocity of the center mass is constant, so is the kinetic energy of the center mass. But notice how low it is. It's the lowest part of this thing. So we have a higher kinetic energy. It dips down and then goes back up again. And the amount of drop corresponds to the internal energy, and that's given as shown here. So this value of change in kinetic energy corresponds to the area under this curve. All right. Now let's consider total inelastic. So we have our K versus T graph, force versus separation, and this time we'll show the force separation curve being the same. And as they collide, it once again diminishes the separation to the minimum, but in a totally elastic collision, there's a major difference. And it'd be better to show this to you, but if you think of two objects, say two lumps of clay, striking each other and mushing into each other, when you start to pull them apart, as soon as that separation goes from minimum to a little bit more than minimum, if there's no elasticity, like with two lumps of clay hitting each other, they'll stay deformed, and instantly as you separate them out from the minimum, they separate. They aren't touching each other anymore. And if they're not touching each other anymore, what is the force between them? That's right. As soon as the separation increases, immediately the force goes to zero. And then it stays there as the separation continues. So this is a very, visually graphic way of showing that. Now, what's the area under the graph formed by no force times this amount of meters of separation change? Well, that's zero, isn't it? That means no work is done. No work is done on the outbound path on the carts. So what does this area correspond to? Well, we do have, on the inbound, force times separation difference, and that's this area. But the energy had to go somewhere. So that's internal energy. But it's not stored as potential. If it was stored as potential, and I could make it yellow, then it would be able to do work on the way out like this did. It did work on the way out. This can't do any work on the way out. So where'd that energy go? Heat. It warmed the thing up. That's not mechanical energy, so it's not usable to do work. So we have kinetic, total, and then it dips down, but it doesn't spring back. We have no potential energy to convert back to kinetic. So we have this internal energy again, and you'll notice in the illustration I've made them the same, but this internal energy this time is not stored potential, but it's heat. And here we once again have the kinetic energy of the center of mass as well, which is the same as before. And the two-cart system will move along at this constant speed, which is the kinetic energy of the center of mass. That speed you could get by conservation of momentum if we had a quantitative problem illustrating this situation. And now let's consider semi-elastic collisions. And getting used to this now. We have a kinetic energy time graph, and we have a force separation plot that as they come together, the force increases in some typically complex way. And then on the outbound, when they separate, it follows a different curve. But unlike the completely inelastic collision, the force does not immediately go to zero. So you'll notice it doesn't immediately drop to zero, but it's at a lower level than the inbound path. Okay, the force was greater pushing against each other than on the outbound. So on the inbound, more work was being done. On the outbound, less work, but nevertheless, actual positive work. So between these two is the loss. Okay, so that's heat. And the part on the outbound, where you're doing positive work, that really corresponds to, where did that energy come from? Where it came from the stored potential energy. That's what enabled it to do work on the outbound. So, kinetic energy total, it dips down. This is the kinetic energy of the center of mass. And what else, though? Positive work is being done to boost that kinetic energy back up. But under this whole thing here is how much was lost. So it dips up. It dips up part ways. So that's what we get after. So this corresponds to the internal that we get back. This is the yellow area. This is the internal energy that's potential. And then the part that we didn't get back is what's lost. And that's internal energy in the form of heat. So those are the typical kind of collisions. But before we leave this topic, there is one more type of collision that I want to address, and that's the possibility of a superelastic collision. So what's a superelastic collision? Well, you could probably surmise that it's cooler than a elastic collision, because it's superelastic. So it's even better than that, whatever that means. Well, let me help you. Let's look at the kinetic energy plot that would result. So here's the total kinetic energy of the inbound cart, say. And then there's an interaction where some of the kinetic energy is lost, but then it gains, and it gains even more than it had in the first place. So in the final situation, you have more kinetic energy than you started out with. Is that violating the principles of physics? No, but there has to be an explanation for it. And so you'll want me definitely to illustrate this for you. But in the analysis, we have the kinetic energy of the center mass right there. And then this. Well, this is all internal energy, and it's the good stuff, right? It's the energy we get back as kinetic. So let's see where this how this happens. I have the same curve as above, but the inbound now is the lower one. In other words, during the collision, we have force and separation, and then on the outbound, when the separation is increasing, they're pushing on each other harder. For any given separation position, they push on each other here not as hard as they do on the way out. So we're getting more positive work in the second half of the collision than what's lost in the first half, or I should say what's stored in the first half. So what about this area in between? The difference between those is this area. That's the difference between what we get coming out and what we had coming in. You know, the area under this graph minus the area under this part of the graph gives you what's here. So this is actually additional U. Yeah, additional potential energy that's obtained as a result of something within the system. And so that the something that's within is the interesting part. That could be additional stored spring potential energy that's triggered upon the collision, and it then releases its potential to produce kinetic. And there's various ways that can happen. It could also be a rocket engine. A rocket engine giving a thrust that then results in a higher level of kinetic energy afterwards than before.